Today's presentation is about light. Here are the key questions for this module. How are refraction and dispersion demonstrated in light? Among the different colors of light, which is bent the most and the least? Why do we see spectacular events in the sky like rainbows, red sunset, and blue sky? When you were in grade 7, you were able to perform activities like my spectrum wheel, colors of light, colors of life, and light up straight. In color of light, colors of life, you were able to explore characteristics of color lights and observe color combination. You were able to compute for the speed of each component of light by using the frequency and wavelength of each color. You were able to describe that visible light is the only electromagnetic wave in the electromagnetic spectrum that can be seen by the human eye. Have you experienced playing a game of looking for a coin or finding a coin while you are in a swimming pool? Can you find a coin easily? Or when you go to the position where you see the coin, is the coin really there? Or you only witnessed optical illusion? This phenomenon can be explained in terms of refraction. Refraction of light is the bending of light when it travels from one medium to another of different optical densities. This can be demonstrated when you place a pencil or a ball pen on a glass of water. It appears that the ball pen or the pencil is broken. Similar to this picture. Or when you look above an aquarium, you see the fish to appear here. But the fish is not actually here, but at this position. So these optical illusions can be explained in terms of refraction. Now, how does light bend? We should first know what optical density is. Optical density is the sluggishness or slowness of the atoms of a medium to maintain the absorbed energy before re-emitting it. Like for instance, if the optical density of a material is 1, the light intensity of 100% when it passes through this material will only transmit 10% of the incident light intensity. Suppose that the density is 2. The 100% incident light intensity will be reduced to 1. And when the density is 3, the 100% incident light intensity will be transmitted at 0.1. So this is how optical density affects the light intensity incident on a material. As the optical density increases, the transmitted light intensity decreases. A known indicator of the optical density of a material is called the index of refraction. So the index of refraction has a symbol small letter n. And the index of refraction can be computed using the formula speed of light in a vacuum, c, divided by the speed of light in the material, v. So the formula for the index of refraction n is c over v, where c is the speed of light in the vacuum and v is the speed of light in a material. The value for speed of light in vacuum, or c, is 300 million meter per second. In your activity later, you will be solving for the index of refraction. So when light crosses the boundary of two media of different optical density, a change in speed takes place. This change in speed is manifested as bending of light. Like for instance, if light travels from air to water, air has a lower optical density than water, so when light strikes the boundary, there is a change in the speed of light. So the speed of light will decrease because water has a higher index of refraction and higher optical density. So when the optical density or the index of refraction is high, the speed of light will decrease. So since the speed of light will decrease, you will see that there is a change in the path of the light ray. So this change in the path of the light ray causes the bending of light. This is also an example. So if you have a coin at the bottom of a beaker, it will reflect light. Take note, we see things because things reflect light. So the reflected light coming from the coin will reach the boundary between water and air. So since there will be a change in the optical density between water and air, so there will be a change in the speed of light. So the speed of light will increase because it travels from a medium of higher optical density to a medium of lower optical density. So since the medium of lower optical density, lower index of refraction, will give the speed of light to speed up or to increase. So the increase in the speed of light will cause the bending. Now, when the light enters, the refracted light enters the human eye, the brain perceives the light traveling to be in a straight line. So, the speed of light increases, light ray moves away from the normal line. So, in order to say that there is a speed increase or an increase in the speed, the refracted ray will move away from the normal line. Take note, this normal line is an imaginary line, so this is broken, that is perpendicular to the boundary between the two media. So, I'll repeat. So, from the coin, the reflected ray will touch the boundary between water and air. So since air is of lower index of refraction, lower optical density, the speed of light will increase. So when the speed of light increases, light ray moves away from the normal line. Okay, so imagine this one. So if this is the incident ray, it is close to the normal line. Now, when the speed increases, it moves away from the normal line. So, the light will enter the human eye and the brain will interpret it as a straight line. Okay? So, the light will be extended and the coin appears to be here. Okay? Similar to this pencil. So if this is the incident ray coming from the tip of the pencil, okay, so it will travel from the water to the air. So the speed of light increases. The light ray moves away from the normal line. Okay, so this is now the evidence that light ray moves from the normal line comparing to this one. So there is an increase in the separation between the refracted ray and the normal line. So now the refracted ray will reach the human eye. The brain will interpret it to be traveling in a straight line. So the image of the pencil appears to be here. So it appears broken.